I am Dr. Harishankar Srivastava from IIRS, working here as Group Head Program Planning and Evaluation Group. And today I am going to talk on GNSS reflectometry and its applications in soil moisture, soil depth, and water level studies. Now, what is GNSS? Means Global Navigational Satellite System. GNSS satellite, actually they orbit Earth once in every 11 hours 58 minutes and 2 seconds and at a medium orbit altitude. And each satellite, irrespective of its age or the technology, each satellite transmits coded signals, and these signals contains the satellite's precise orbit details and a very stable time stamp from an atomic clock. While GNSS satellites may vary in age and design, their principal operation remains the same. GNSS satellites, they transmit two carrier waves in L band, which is normally referred to as L1 and L2, and these carrier waves transmit information from the satellite to Earth. Most of the GNSS receivers have two parts. First is the antenna and the second is the processing unit. Antenna receives satellite signals, which the processing unit makes sense of it to determine the position of the GNSS receiver. And minimum 3 satellites are required. It needs to collect information from a minimum of 3 satellites. When the receiver in our antenna, this system, when the receiver knows the precise position of itself with respect to each satellite, that must be at least 3, it transmits its own position into an Earth-based coordinate system, that is latitude, longitude, and altitude. So normally this GNSS scientists were using to know the exact location and the height of that point. And this is the GNSS receivers. But a more recent technique of using GNSS for the retrieval of geophysical parameters is the GNSS reflectometry. Now the GNSS reflectometry, it involves making measurements from the reflections from the Earth's surface of navigation signals from satellites like global navigation satellite systems, for example GPS or our own Indian IIRS. Now what is GNSS reflectometry? It is deliberately bouncing signals. The technique, something to learn about. It can be related to ocean properties, it can be crop height, it can be snow depth, it can be water level, anything. Now GNSS reflectometry is an innovative technique that exploits GNSS signals reflected off surfaces as signals of opportunity to infer geophysical properties of reflecting surfaces. Now, if we are trying to use GNSS to retrieve geophysical parameters, then it is also remote sensing. So if we compare the conventional remote sensing with GNSS reflectometry or GNSS remote sensing, then what are the advantage and disadvantage? The first advantage is excellent temporal sampling and global coverage as far as this GNSS reflectometry is concerned. Long-term GNSS mission life and they are very cost effective. If we compare with the L-band actual radar system, then it is very cost effective because we require only a receiver. Now, what is the historical perspective? In traditional GNSS application, signals arriving at a receiver's antenna from nearby reflecting surfaces, which is known as multipath interference, with the signals received directly from the satellites, which can often result in a reduction of positioning accuracy. So these multipath signals, which is the key for GNSS reflectometry, they were a noise for those users who are only interested to measure the location and height. Concept developed over last 2 decades, that is a GNSS transmitter together with a receiver capable of processing GNSS scattered signals of opportunity. We can compare it as a bistatic radar, because normal synthetic aperture radar system, it's a monostatic radar, but in GNSS we can consider it as a bistatic radar. Then by properly processing the scattered signals, this system can be configured either as an altimeter or a scatterometer, allowing us to estimate characteristics of land or ocean surface such as height, roughness or dielectric properties of the underlying surface.
Sir, slides are still not moving, sir.
Slide बॉस मैं मूव नहीं कर रहा हूँ.
Okay.
अभी मैं मूव नहीं कर रहा हूँ, आप चिंता मत करो. मैं by 4 o'clock by our time, my time, I will finish between 4 to 5. Depending on the platform of the GNSS receiver, that is stationary, whether it is stationary or airborne or spaceborne, the capabilities of this technique and specific methods for processing of the reflected signals may vary. There are 2 major methods. One is actual dual receiver based reflectometry, and that is also known as direct method. And the second one is using single receiver, and it is known as interference method, IIR method. Now, the direct signals received by the GNSS antenna are right-handed circular polarized signals, also known as RHCP, whereas the reflected signals coming from the reflecting surface are left-handed circular polarized. So if we are using 2 antennas, and one is looking vertically up in the upward direction and one is looking up vertically in the downward direction, then the signal, then the direct signals which are coming towards the receiver are right-handed circular polarized signals, and the reflected signals which may come from a crop covered field or a bare field or from snow or water surface or ocean, that are left-hand circular polarized signals. The signal to noise ratio of direct signals are being used for system calibration. Now one can think that when we are interested only in the reflected signals, then why we require 2 antenna, or what is the use of the direct signals? Because direct signal is not going to give you any information about the soil moisture or snow depth or water level. Then why to use this direct signal? Direct signal we are using for the calibration purpose. These direct signals we are using for the calibration of the reflected signals, which are being used for retrieval of geophysical parameters using power ratio of left hand circular polarized reflected SNR over right hand circular polarized direct SNR. Alternatively, the approach of estimating reflection coefficient and reflectivity will also be utilized for retrieving these geophysical parameters. Now, as I told you that there are 2 methods. One is direct method and other is that interference method. If we have only one receiver, then we have to use this interference method. And here in this case, although this method is little complicated and it is not a straightforward method, you have to develop your own algorithms, and the separation of reflected signal from the direct signal is a big challenge in this case. But in this case, the receiver is very cheap. Cheap means something between 12 to 15 lakhs, Whereas if we are using dual antenna, dual receiver, then in that case the cost may go up to, it is very costly. It may go up to 75 lakhs, 90 lakhs, like that. So that is why this GNSS IR method is also very useful, looking at its cost effectiveness. In this case, the antenna receives two signals, direct signals and reflected signals. And the interference of these two signals causes multipath, which is a useful signal for GNSS interference reflectometry method. The multipath signal constructively and destructively interferes with the direct signal as a GNSS satellite rises or sets. One can characterize the expected interference pattern from a horizontal planar ground reflection by a sine wave with a constant frequency. The constant frequency depends on the height of the antenna's phase center above the reflecting surface and the GPS wavelength and sine of the elevation angle. Now this slide is showing the geometry and footprints of GNSS satellite. This slide is very important from the point of view that the user should know that at the time of validation as well as at the time of model development, suppose he or she is interested to retrieve surface soil moisture. So at the time of model development, because we have to have the ground soil moisture values, or at the time of validation, he should know that signals are reflecting from which area. So this slide is, from that point of view, this slide is very important. GNSS IR footprint is also called as fresnel zone for an individual GPS satellite track is represented in this diagram. The fresnel zone is a narrow ellipse that depends on the antenna height and elevation angle. As satellite rises, the fresnel zone becomes smaller and closer to the antenna. You can see in this slide that the size of these elliptical sensing zone are directly sensitive to height of the antenna. Height of the antenna, I am not talking about the satellite. I am talking about the antenna which we have mounted on ground. So its height can be 1 meter, 2 meter, 3 meter, but normally we try to use optimum height of say 2 meters. The satellite elevation angle and the GNSS transmitter frequency, it is a function of this elliptical sensing zone is a function of antenna height and elevation angle and the frequency. The orientation of the fresnel zone with respect to the GNSS antenna depends upon azimuth angle also. Now, what are the things that we can attempt using GNSS reflectometry? If we are interested in ocean, then ocean altimetry we can do. We can know about the sea state. Over land, we can do soil moisture retrieval, vegetation height retrieval. Over snow, we can measure the snow thickness, or in other words, snow depth. And for inland water, it can be a wetland, it can be a water body. We can also measure the water level. Now, this is a typical example of that. I told you that two receiver system, or this is a real actually GNSS reflectometry. Here you can see that one direct signal is coming and one reflected signal is coming. Now, the concentric dashed circles indicate power levels. These levels of receiving antenna. For an incoming GPS signal of say power P, the direct signal will enter the gain pattern at an angle equivalent to the satellite elevation angle. So what I want to convey that this direct signal which is coming, in this case the amplitude, because in this case the elevation angle is positive, it is much higher as compared to the case where the reflected signal is coming, because in that case the elevation angle is in negative. GPS signal phasor diagram describing carrier tracking loop operation with a direct and reflected signal. The I and Q axis indicate in phase and quadrature components of the signal respectively. The three phasors represent the direct, multipath and composite signals with amplitude. AD means direct, AM is multipath respectively. The phase of the direct signal is represented by Tesla D, and the phase of the composite is Tesla C. Now, this slide is showing how to determine the SNR multipath amplitude. The multipath contribution to SNR needs to be separated from the direct signal's magnitude. This is very important and most complicated component of using single antenna GNSS reflectometry, which is popularly known as GNSS IR, because separation of direct signal, separation of reflected signal from the direct signal, it is a very critical and very complicated task. Multipath contribution to signal to noise ratio is small in magnitude but oscillatory, while amplitude of the direct signal is large in magnitude but goes through a complete cycle only once over a satellite pass. Large magnitude trend is equivalent to AD, and removing it, the multipath contribution to SNR is isolated. These are the methods. These are the methods in very simple language. It looks simple, but it is very complicated. And similarly, the gain effects are accounted for by removing a low order polynomial to arrive at multipath oscillations whose amplitude is proportional to the surface reflectivity. This slide shows comparison of GPS multipath amplitudes and volumetric water content. This is between observed and estimated by this technique. Multipath phase for soil moisture estimation. When the soil is wet, the apparent reflector is close to the surface. Means if soil is wet, the water is at or near the soil surface. And we know that the dielectric constant of water is very high as compared to dry soil. It is around 80, and the dry soil dielectric constant is 3 to 4. So when we start adding water, or when we start doing irrigation in a dry field, its dielectric constant may increase from 3 to 4 to up to 30. So as the dielectric constant is increasing, or as the moisture content is increasing, the apparent reflector, which is going to reflect the incoming signal, comes closer to the upper surface. As it dries, and when the soil is drying, this reflection depth will go in the deeper layers. So when the soil dries, the reflection depth is several centimeters deeper as compared to the top surface. So it creates a multipath, and this multipath phase is sensitive to the very fine frequency changes expected from small changes in apparent reflector depth. The change in soil moisture affects the multipath phase of the signal to noise ratio. Since the relative antenna height is constant, because our height is constant, and this reflector height is going down in case of dry soil and going up in case of wet soil. Since the relative antenna height is constant, changes in height of reflecting surface, the reflecting surface can be anything. It can be soil due to soil moisture. It can be vegetation height. It can be snow depth. It will modulate the signal to noise ratio. The change in the signal to noise ratio is related to change in nature / state of the surface. The multipath SNR can be expressed. This is the formula to calculate the multipath signal to noise ratio. Now here you can see that we have plotted phase with the volumetric water content or soil moisture, and this phase of multipath signal to noise reflectivity, it is very important, and in next few slides I will indicate how this is used to retrieve volumetric soil moisture. Now, how to estimate soil moisture using GNSS reflectometry? Right hand circular polarized signals usually increases the SNR when the satellite elevation angle increases. We know that this right hand circular polarization, it refers to the direct signal, and left hand circular polarized is related to reflection coefficient of the reflecting surface, which is in turn related to the water content of the reflecting surface topography, roughness, and the satellite transmitted power. The volumetric soil moisture can be estimated using phase change of signal to noise ratio as given below. Here you can see this slope, S is the slope of volumetric soil moisture, and means it is the slope indicating the slope of a curve which we can plot between volumetric soil moisture and phase shift for multipath SNR reflectivity. The slope of the VSM and delta phi curve should be derived for more sites. This is very important. Actually, based upon just one site and one curve, we may not be able to retrieve volumetric soil moisture with high accuracy. So it is always advisable that we should take more than one test site, and we should generate the curves based upon a time series data. Time series means at least 2 month data we should require to plot and then to estimate the slope which we can use for soil moisture retrieval in this equation. There is one more method where we can generate soil wetness index. Alternatively, the phase time series can be normalized for each satellite track. So alternatively, the phase time series can be normalized for each satellite track, and using slope is not needed. We consider the median value of the normalized phase from all available satellites, and we can generate this soil wetness index, which is given by this formula. This volumetric soil moisture could then be estimated from phi index or wetness index. Now here you can see three validation curves I am showing. In the first curve, this curve you can see that there is a very poor agreement between the observed soil moisture value and the retrieved soil moisture value. It is due to the reason that we have used a priori slope value in this case, in this study. Whereas in the second case, or this B, here you can see that the validation has improved significantly from A, and observed value and estimated values are in good agreement with each other, because here we have used locally adjusted slope value. And in the third slide, or the C1, you can see that in this case there is a perfect agreement between the ground measurement of soil moisture and retrieval using GNSS reflectometry method. And you can see it is due to the fact that in this case we have used soil wetness index for the retrieval of volumetric soil moisture. This curve is also showing a scatter plot of daily mean in situ volumetric soil moisture observations at a depth of 5 centimeters. Now, soil moisture can also be retrieved. Okay, now I am going to talk about the interference pattern technique. Here you can see that simulated interference power received versus reflectivity we have plotted, and you can see that Brewster's angle value matches with notch position 29 degree. In the case of bare soils, the interference power presents only one notch, which is due to Brewster's angle, the angle at which total transmission occurs for the vertical polarized wave. The Brewster's angle is then a function of the soil dielectric constant, whose value highly depends upon soil moisture. Now, if we are using single antenna, we can also use, instead of that right hand circular polarized and left hand circular polarized, we can use vertical and horizontal polarization also. And one more important thing is that if we are interested in soil moisture retrieval using GNSS reflectometry or GNSS IR method, we should always use low elevation angles. Why? Because so that the interference of these two signals, direct signals and reflected signals, they should produce a coherent addition with varying phases depending upon the elevation angle. So if the elevation angle is low, then we will get constructive or coherent addition of their phases. We may also change the polarization basis from circular to vertical or vertical and horizontal. And one thing that happens in this case at vertical polarization, there is a magic angle for which reflection coefficient vanishes. And this angle is known as Brewster's angle, and it depends upon the dielectric constant of the surface. A dielectric constant is nothing but the soil moisture. Now, coming to the snow depth and water level retriever, the change in relative antenna height. Suppose if we have installed an antenna in a place where that place is prone to snowfall, but at that time there is either no snow or no snow depth. Now, when the fresh snowfall will occur, this relative height of your antenna will decrease. So this change we can measure. This slide tells about that fact. The change in relative antenna height due to change in snow depth or water level. If we have installed our antenna near to a water body or in between a water body, then the change in relative antenna height due to change in snow depth, water level or vegetation height can be retrieved by using dominant signal to noise ratio period, TD, the peak period of the average power spectrum received from the wavelet analysis of signal to noise ratio using this following relation. By using this relation, we can estimate the change in height, and that is nothing but the snow depth, you can say, or change in water level or change in crop height. Now, effect of the snow thickness. It is found here in these two slides. The number of notches increases and their position also when snow thickness increases. In first slide, you can see that there is only one notch, and in the second slide, there are 3 notches. So when the snow thickness will increase, the number of notches will also increase. Here also you can see this snow depth variations estimated from GPS reflectometry or GNSS reflectometry. We have plotted with the actual measurement on ground, and you can see, although it is not perfectly matching, but it is in good agreement with the ground results. Effect of this height parameter: when the antenna is closer to the surface, the frequency of the oscillations versus the elevation angle is lower than when the instrument is at a higher height. And this is the very reason why we are getting more notches when this relative height of the antenna is decreasing. Similarly, we can also estimate water level, and the concept is same. Here you can see that it's a observed versus estimated plot indicating the water level. Crop height estimation also we can measure, and here you can see that 3 graphs are there. One is in graphical way, other is in this relative. Actually, in one graph, from signal point of view, the information is presented, and in another graph, in graphical form, the information is presented. But the main thing is, bare soil produces only one notch. Means if there is no crop, then we will get only one notch. And if crop is there, say for example 60 centimeter, then it has produces 3 notches. And when the crop height further increases and it goes up to 90 centimeter, then we got 4 notches. So this number of notches indicates that the height is increasing. This height can be anything. It can be snow depth also, thickness also, as well as crop height also. And these are the few references. If anybody is interested, he can go through these references. And although limited literature is available in this field, but still very good papers are available, and a few I have mentioned here. You can go through these papers. So thank you so much.